Okay, here's the gist of the binomial approximation. It says that 1 plus some number to the factor of n is approximately equal to 1 plus nx if x is much, much less than 1. So let's say that again. 1 plus x to the n is approximately equal to 1 plus nx for x much, much less than 1. Well, where does that come from? So you learned in elementary school how to raise a plus b to the n power. Actually, you probably didn't learn in elementary school. You probably learned it in pre-calculus, but that might as well have been elementary school. So how do you raise a plus b to the n power? Well, you might have learned, or you might remember that you've seen at some point that this is, and you know how to do this, no matter whatever a and b constants are and what n is. But anyways, this is the general equation for the binomial expansion or binomial theorem. Whoops. Right, let me write this down. A n minus 2 b squared plus dot dot dot. Okay, plus b to the n. So the question is if I have 1 plus x squared, what's 1 plus x squared? Or it doesn't, x plus y squared. What's x plus y squared, right? X plus y squared is equal to x plus 2xy plus y squared. Whoops. It would be x plus 2xy. This would be 0 and plus y squared, right? That's x plus y squared. And you know how to do x plus y cubed. It's going to be x cubed plus 3x squared y plus 3y squared x plus y cubed. I think I'm just trying to do this in my head. But you know how to do the binomial expansion. And then when you get up to higher powers of n, it follows a pattern. And that pattern, you might remember, we're not going to go into it, has to do with Pascal's triangle. Pascal's triangle gives you the coefficients, right? The coefficients that are in front of each of these terms. Okay, we're not going to worry about that. Notice we only care about we don't care about, when we're doing the binomial approximation, we don't care about all these terms. Let me just show you why. If I divide through by a to the n, factor out an a to the n, what we end up getting is, if I factor out an a to the n, not a sub n, a to the n, so we've got 1 plus b over a to the n equals 1 plus n b over a plus n times n minus 1 over 2 b over a squared plus dot 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 b over a to the n. Whoops, not squared. Plus b over a plus b over a to the n. Okay, so if we factor out an a to the n, we get that. Hopefully you caught that I didn't factor out the a to the n on this side. I only factored out on the other side. And so those two cancel. Okay, so we've got 1 plus b over a to the n equals 1 plus n b over a plus n times n minus 1 over 2 b over a squared. And then there's going to be some order b over a cubed term and higher. And then, right, in the last term is going to be b over a to the n. Okay, so I just want to point out a couple things here. One is we've got b over a to the first, b over a to the second, and then this just means some term with b over a cubed, b over a to the fourth, b over a to the fifth, order b over a cubed, and higher, all the way up to b over a to the n. And then there's some coefficients in front of each, n times n minus 1 over 2, n times n minus 1 times n minus 2 over 6, etc. There's going to be terms, other coefficients we're not going to worry about. We don't care about those coefficients. Okay, so what happens if b over a is much, much less than 1? Well, if b over a is much, much less than 1, then don't worry about what n is. N is, it's not going to be a very small number necessarily. It could be anything. N could be anything. So let's not worry about what n is right now. But notice that, let's just make n equal to 1. And notice that the first term after the 1, this first term, oh, and by the way, just in case you're not following along, let's just do this. B over A is much, much less than 1. That's the same as saying, in this case, x is much, much less than 1, because here we're saying 1 plus x to the n. Here we're saying 1 over b plus a, 1 plus b over a to the n. Okay, so the thing to notice here is that this first term, which I put in the yellow box, is going to be, because b over a is much, much less than 1, this first term must be much, much less than the first term. So the big question here, what I'm trying to get at, is what about the second term? How does the second term compare to the first term? Well, if b over a is much, much less than 1, then what's b over a squared compared to 1? It's so much less than 1, right? And then what about the third term? b over a cubed. If b over a is much, much less than 1, then b over a cubed is that much more less than 1, cubed. So what do I mean by that? Well, let's just say that b over a is 0.01. That's not much, much less than 1, but let's say it's 0.01. Then the first term, let's do a different color. The first term is going to be order 0.01. The second term is going to be order 0.01 times 0.01, 0.0001. And this one is going to be so we've got, let's go ahead and write this out. So we've got the 1 up front, right? The 1 up front. Plus, and forget the n's for now, 0.01, if b over a is 0.01, plus 0.0001, plus 0.000001. Is that 0.01 to the third? I think it is. And go on and on and on. So in the end, we have 1.010101010101 dot dot dot. So if we expand that, we've got that. So so here's the question: is did we really need? This is the first term after the 1. This is the second term after the 1. This is the third term after the 1, or that's also the power of b over a. Did we need the second term? Well, we needed the second term if we want to be that accurate. But but that's, what's the difference between 1.01 and 1.0101? It's not a very big difference, right? That's a 0.01% difference. And therefore, did we need the third term? Did we need the fourth term? Did we need the fifth term? Did we need the sixth term? And the answer is, it depends how accurate we want to be. But in this case, remember, b over a was not much, much less than 1. If b over a, let's just say for v over c, we know that the velocity of the ether and also the velocity of any measurable object on Earth that's not in an atom smasher is going to be much, much less than c, to the point where it's about v over c is if c is 3 times 10 to the 8th, and what's the highest velocities that we've got that aren't atoms and accelerators? The highest velocities we've got are at best 10 to the 4th, right? So v over c is about 10 to the minus 5. So it's not just 10 to the minus 2, it's 10 to the minus 5. So that's 5 decimal places, right? So think about it. So when we do the binomial expansion, not the approximation, when we do the binomial expansion, we've got the 1 is what's called the zeroth order expansion. Okay, let me go. The 1 is called the zeroth order expansion, right? And this is the first order, second order, third order, right? So the 1 is the zeroth order. If we go to first order, we're just going to get an additional 1, 2, 3, 4, 5. Now, if that's just the first order. That's the first order expansion. That's just 1 plus nx, or 1 plus n v over c. Well, let's make that a little neater. So the second order expansion gives us another decimal point, another 6 decimal points over, another digit, another 6 decimal points over. When in this world do we ever need to be that accurate? 1 out of 10, what's it called? It's 1 in 10 billion, right? That's 1 in 10 billion. we rarely need to be that accurate. So we rarely would ever need to go out to the second decimal place. Hence, the binomial expansion says that if b over a is much, much less than 1, this quantity to first order is good enough. Not only is it good enough, it's really good enough. Because that next decimal place is so far down the line that we could never be that accurate. So, what the binomial approximation is just taking the first order. So the zeroth order, so 1 plus x to the n is approximately equal. The zeroth order is 1. If x is much, much less than 1, indeed, it is approximately equal to 1. It's not much different than 1, and that may be only as accurate as we need to be. But if we want to see how different it is from 1, this is really key. How different this value is from 1, you will see later that is going to be that's going to be necessary. Then it's approximately equal to 1 plus nx for x much, much less than 1. And we will rarely, if ever, probably never, care about the second order terms, order x squared and higher, are truly insignificant. Okay, I know I'm getting a little repetitive, but one more time. The reason why we want to do the binomial approximation and we want to carry it out to first order, zeroth order, first order, is because it is true that 1 plus x to the n is approximately equal to 1 to zeroth order. But we often want to see what the difference is from 1. 1 minus 1 plus x to the n. We want to see how much accuracy we gain by going out to first order. So 1 minus 1 plus x to the n is indeed equal to 0 to zeroth order. But 1 minus 1 plus x to the n is equal to nx to first order. And that is something that we're often interested in. So be careful about when you're asked to approximate whether context dependent, whether you want to go to zeroth order or whether you want to go to first order. Okay. A couple other quick things to note is that you can look back at the binomial approximation and you will see that if there's a minus sign, that doesn't change anything. 1 minus x to the n is approximately equal to 1 minus nx. So you could just say 1 plus or minus is 1 plus or minus. And so therefore, let's say, for example, 1 over the square root of 1 minus v squared over c squared. What's that approximately equal to? Well, it's equal to 1 minus v squared over c squared to the minus 1/2. So therefore, it's approximately equal to 1 minus, you bring down the power, minus 1/2 v squared over c squared. And therefore, that is equal to 1 plus v squared over 2c squared. So that's how to do the binomial approximation. So we can go back to the Michelson-Morley experiment, and we can say, okay, now we know how to fill this in. This is going to be pause here and try to do the binomial approximation on these two fractions. But now I'm going to go ahead and write it out for you. So if you want to do it yourself, pause. But it's going to be 1 plus 1/2 v squared over c squared. That's the binomial approximation on the first, minus 1 plus v squared over c squared is the binomial approximation of the second. So that key time difference in the Michelson-Morley experiment due to delta t is equal to, and it's not only approximately equal to, it really is equal to, because the approximation is so good that we don't even have to worry about loss of accuracy. Because that loss of accuracy would be in like the 10th decimal place or the 12th decimal place down, which is never going to be measurable in any experiment we do, well, anytime soon. Okay, so we can go ahead and multiply this out, and we get minus 1/2 v squared over c squared. And so that ends up being LV squared over 2c cubed with a minus sign. All right, what does the minus sign mean? Well, the minus sign means is that one is fallen behind the other. So the minus sign is actually irrelevant here, right? One's ahead of the other by LV squared over 2c cubed. One's behind the other by minus LV squared over 2c cubed. So again, this is just a time difference when we shift the thing 90 degrees. So this, the absolute value of this number, LV squared over 2c cubed, is what's important. Okay.